Good afternoon. We'll wait for a few minutes for other people to join. Okay, we will start the session. Welcome to the live session 10 with me, Mahalakshmi S, Research Scholar from NIT-Trichy for the course Basic Environmental Engineering and Pollution Abatement. So this is the general information. This live session for the course Basic Environmental Engineering, Pollution and Abatement will happen every Saturday from 3 p.m. to 5 p.m. And you can join the class by using the Gmeet link MDI VDCP NCG. So I will be handling the Saturday session from 3 p.m. to 5 p.m. And all the live session videos are recorded and uploaded on the YouTube channel name Mahalakshmi S. You can find it through at Mahalakshmi Shekhar and NIT. I hope I am audible. Shall I continue?
Yes, ma'am, you are audible.
Okay, thank you. So now first we will discuss the week 9 assignment solution. Then we will come to the week 10 overview and then some sample questions and sample problem for the week 10. So the first question of assignment 9 is sludge generated from chemical precipitation and sedimentation in primary clarifier is called as. So these are all very basic questions. So now, in the question itself, it is mentioned like the sludge is generated in the primary clarifier, right? So in the primary treatment, some of the steps involved for the primary treatment are mainly the gravity-based settling, which is nothing but sedimentation, and then sometimes we can do chemical precipitation. So in this primary treatment, in the primary clarifier, the sludge is produced. So absolutely, the answer is primary sludge. Okay. Next question is identify the following operation. So in this one, there is two parts A and B. Into the A, the primary sludges are going inside, and into the B, the secondary sludges are flowing in. And then from the A and B, all the outputs are going for the further processing. Okay, they are asking you to identify the operations in the step A and step B. So we have already discussed like the gravity thickening is the method which is commonly used for the primary treated sludge. So A is the gravity thickening and B is the flotation. So flotation is very important. Most of the time in the secondary treatment process, we use the aerobic treatment with the help of microorganism. We are going to degrade the all the organic contaminants. So whatever the sludge produced in the secondary treatment is again fed into the flotation process to separate the flocks easily. Okay, and then these are all further process. So A is gravity thickening. The gravity thickening is most commonly used in the primary treatment only. Okay, and B is the flotation. Next question is dewatered sludge contains a significant amount of water. So dewatered sludge. So what is this dewatered sludge? So from the clarifier, we are going to separate the sludge at the bottom and we are going to collect the fresh water from the top. Right. Always the fresh water goes to the top and the sludge is coming at the bottom. So, however, you are separating the sludge from the fresh water, there will be some amount of moisture content present in it. So, in this dewatered sludge, how much amount of water is generally present there as? So, it is about 70 percentage. Next question is digestion of the sludge can be helpful to reduce the total mass of solid, destroy the pathogen, make sludge easier to dewater, all of the above. So the right answer is all of the above because the sludge digestion involves both reduction of the total mass of solid content because this anaerobic digestion of the sludge will result in the formation of carbonaceous matter into carbon dioxide and methane. So the mass of the solids are reduced. And then during the anaerobic digestion, at the particular pressure and temperature, the pathogens are also getting destroyed. And then the sludge make the sludge easier to dewater. So this is also included in the digestion of the sludge. Okay, so all of the above is the right answer. Next question is, which of the following is not a primary product of anaerobic digestion? So in the anaerobic digestion, as I have mentioned, we use the digester, right? So this is the digester setup. So into this digester, the sludges are present at the bottom. And what happens in the top, the release of the gaseous component will occur. Okay. So what happens here? All the biogas are collected from the top of the digester, and then the biogas and also the hydrogen are all collected from the top. And whatever the leftover sludge present here can be again used as the composting material. Yeah, the only product which is not coming from the anaerobic digestion is the oil. No liquid product is obtained from the anaerobic digestion. Only the solid compost can be used, and the biogases like methane and hydrogen are all produced from the anaerobic digestion process. Next question is typical hydrolysis product of cellulose are. So once the cellulose is hydrolyzed, what are the products formed? They are asking. So the right answer is glucose and cellulose. So cellulose, when it is hydrolyzed with the help of enzyme or chemicals, it is going to form the simplest form like glucose and cellulose. Next question is which one is physicochemical technology? So question is which one is physicochemical technology for the removal of organic compound from wastewater? Fungal treatment, aerobic treatment, absorption. So in all these three, we use fungi, aerobic microorganism, and anaerobic microorganism are all involved. So all these are coming under the category biological. Okay. So only thing left out is absorption. So this is the physicochemical technology which is used to remove the organic contaminants from wastewater. The next question is which one of the following is the biological method used for the removal of organic compounds from wastewater? So we know adsorption is using some physical chemical technology, and nanofiltration it is nothing but it uses the filters. It is a filter that is used to remove the contaminants. And photochemical oxidation again it is a chemical method. So only biological method is the phytoremediation. We know that phytoremediation uses the plants. Okay. Now match the following feedstock with their typical hydrolysis product. So carbohydrate is hydrolyzed into, we know the right answer. So we carbohydrate is hydrolyzed into alcohol. Okay. So all the carbon compounds along with the hydrogen and oxygen, all these things are going to form the ethanol, right? C2H6O. So it is a alcohol, and cellulose is again broken, and it is going to form the simplest structure like glucose. Okay, and then the protein. So protein is composed of amino acids. So once it is hydrolyzed, it is going to release the amino acid. And peptides, once it is hydrolyzed, it is going to release the fat molecules. Okay. So the right answer is P3, Q4, R2, and S1. Now coming to the problematic question, sedimentation tank is treating 5 mld of sewage containing 290 ppm of suspended solid. The tank removes 50% of the suspended solid. Calculate the weight of the sludge produced per day, assuming the moisture content of the sludge as 90%. So here in a sedimentation tank, 5 mld. So the rate of the sewage water getting treated is 5 mld, and this sewage water is containing 290 ppm of suspended solid. Okay, and then the tank removes 50% of solid. So this is the concentration, and the tank is going to remove only the 50% of the suspended solid they have mentioned, and calculate the weight of the sludge produced per day. How much amount of sludge is produced by assuming the moisture content of the sludge as 90%. For the total concentration of 290 ppm of solid, only 50% is removed. So only that 50% is going to form as the sludge in this sedimentation tank. Okay, in the formed sludge, the moisture content is 90%. The question is to calculate the weight of the sludge produced per day. The right answer is option 1, 7,250 kg per day. We will see the solution. So from the given question, the flow rate is Q is equal to 5 mld, which is nothing but 1 million is equal to 10 power 6. So 5 into 10 power 6 liters per day. Okay. And now the concentration of the suspended solid is given as 290 ppm. So 1 ppm is equal to 1 mg per liter. So it is 290 mg per liter. Okay. Now the concentration of solid produced as the sludge. So 50 percentage is produced as the sludge. It is 50 percentage is the efficiency of removal they have given. So we should find the concentration which is produced as the sludge. For that we have to multiply the efficiency 50 percentage, just nothing but 0.5. 50 by 100 is 0.5. So zero point 0.5 into concentration of the solid. What is the total amount of solid? 290 mg per liter. So it is 0.5 into 290, which is nothing but 145. Okay. So this is the concentration of the solid produced as the sludge. Now, what we need to find is the total dry mass total dry mass of the solid in the sludge. For that, this is the concentration. For every 290 ppm, 50% is removed. It is given. But the capacity occupied in the sedimentation tank is the incoming wastewater is 5 mld. Right. So 5 million liters are treated in a day. So for this much capacity, we need to calculate the total amount of the solids in the sludge. So we have to multiply the flow rate with it. So okay, 5 into 10 power 6 liters per day into 145 mg per liter. So if we cancel this one, we will obtain 725 kgs per day. Okay. Now we know the percentage of moisture content, which is nothing but 90%. Okay, 100 divided by 100 minus 90 is 10. So we know the total mass, which is 725. So 100 divided by 10 is again 10. So we have to multiply 10 into 725, which is nothing but 7250. So that is the total mass of the sludge produced in a day. Okay, in kgs. So the right answer is 7250 kg per day. I hope it is clear. Shall we move on to this week content? I hope there is no doubt. So this week 10 is again the continuation of the week 9. Last week we have seen the industrial pollution control in the sugar industry. And now in this week we will continue the topic the industrial pollution control in various industries. The list of industries we are going to see are the distilleries and then the fertilizer industry, then copper smelting industry, uh, then we have a tannery industry, petroleum refinery and petrochemical industry, then pulp and paper industry. Like this, there are different industries, the different processes involved in these industries, and while producing the end product of each industry, what are the possible pollutants released from these process? These are all the things we are going to discuss in this week 10 lecture. Okay. Coming to lecture 46, it is about the pollution control in distillery. First of all, what is distillery? So if we see this distilleries or the industry which produces the alcoholic beverages, most commonly produced one is the ethanol. So now in worldwide, if you see, The major feedstock used for producing the alcoholic beverages include the coarse grains. Okay, these coarse grains include the rice grains of maize and the corn. All these things are coming under the category coarse grains. Barley, everything will come under the category coarse grains. So in worldwide, coarse grains are the major feedstock for the alcoholic beverages production. Followed by we have the cane juice and then molasses, then wheat, sugar beet. All these are some other feedstock for producing the alcoholic beverages. And some other non-agri products like non-food products are also used for the alcoholic beverages production. This is in case of the worldwide. But if you see particularly in India, molasses, which contain around 40 to 50 percentage of sugar content in it, is going to be the major feedstock in our country, India, for producing the ethanol. So how this ethanol is formed means we use any kind of these feedstock which is rich in the disaccharide. Okay, so disaccharide is C12H22O11. So when it is hydrolyzed, it is going as to give the monosaccharide, which is nothing but glucose and fructose, which is C6H12O6. When these glucose are fermented, so this fermentation is very important because we use two kind of enzymes. Generally, these two enzymes are involved in the fermentation process. Their name is invertase and xylase. Okay. So these two enzymes are involved in the production of ethanol. This is ethanol, and along with it, carbon dioxide is also released. So in the fermentation process, we obtain the ethanol. This is the simple overview of ethanol production. Now we will see the process flow sheet, how this ethanol is produced from the sugar mill molasses. As I said, molasses is the major feedstock in India. How this molasses is obtained means it is obtained from the sugar. Okay, after extracting the sugars from it, we are getting the molasses. So these molasses are weighed and then these molasses are stored in the storage tank initially. Then, when these molasses are used for the ethanol production, initially in a measured quantity, these molasses are diluted with the filtered water. So, first step is dilution of the molasses. Okay. Then this diluted molasses is again mixed with the microorganism called yeast. Okay. Why yeast is used means this is the microorganism that is going to give us the required enzyme invertase and zymase for the fermentation process. Okay, so this yeast is again mixed with the diluted molasses, and this is subjected to the fermentation process. So fermentation is a process where our monosaccharide glucose is converted into ethanol. Okay, so fermentation is going to happen here. So to ensure the fermentation, we have fermentation cooling tower. Like to maintain the optimum conditions for the fermentation, we use more amount of water, right? So for these water addition and all, we are using the temperature control for everything. We are using the fermentation cooling tower, and these distillation cooling tower are all used here. And then what we are doing with the help of this fermentation is we are producing the ethanol. First, whenever we are producing our product, there will be some amount of byproduct also, right? Initially, we will not get the absolute ethanol at the first step itself. So we are clarifying our product. Whatever liquid is produced in this fermentation process, that liquid is termed as the wash. So in the clarified wash tank, so clarification is generally separation of the solid and liquid compound, right? So what we are doing is clarification is happening, like settling is going to happen. Then with the help of the decanter, we are going to separate the wash liquid from the sludge. So whatever the sludge is present here is some amount of untreated or undecomposed molasses. Okay, these sludge can be used as a very good manure. Okay, and again, the only liquid part from the decanter is termed as the wash, is collected to the analyzer column. Then it goes to the rectification column. So whatever product formed from here in the step rectification column is termed as the rectified spread. Okay, it is not very absolute ethanol. It is termed as the rectified spread. Okay, these rectified spread are again stored, received and stored in the storage tank. This is the another byproduct from this one. Our main product is ethanol. So after clarification, we are decanting it, we are separating the liquid which is washed, and this liquid is again going to the analyzer column and the rectification column where rectified spirit is produced. Then again we are going to produce the absolute ethanol by removing the moisture content from our wash liquid. So in the molecular sieve dehydration bed, the water removal is going to happen, and again, after removing the water content, the absolute ethanol is now produced. So whatever the end product produced is received and stored in the tank. So in between, we have many waste streams, which include the spent wash. So the spent wash and the fuse oil, spent lees, all the waste streams. How these waste streams are treated means these are treated in the CPU, which is a condenser unit where all these pollutants are treated. So now the spent was and spent leaves are all treated again here in this process CPU. We will discuss this later. So now we have different stream here called MEE. It is the multiple effect evaporator. So why this evaporator is used means all these waste streams are going to MEE, and this MEE is going to evaporate the wastes. Okay. So after concentration of the wastes, it is going to the boiler. So where these buckets can be used, and again this can be reused when it is collected to the permeate. Once it is evaporated and then finally this permeate is coming, this can be reused, like to reduce the groundwater utilization. These permeate are reused for the fermentation process itself. And whatever the thing which is rejected here after the treatment also, whatever is rejected here is again going to the CPU for further treatment of the waste stream itself. So these waste streams are initially going to the evaporator chamber. It is trying to be recycled. When it is rejected, it is coming to the CPU for further treatment. And when it is permeate, it is again used for the fermentation process itself. So this is the basic overview of the processes involved in the ethanol production. So here, if you see what could be the waste product streams. So as I said, the spent wash, spent leaves are all the major waste streams. Apart from that, there include some air pollutant like mainly from the evaporators, the air pollutants can come, and the steam leakages and steam venting can cause the noise pollution also. So now each and every waste stream is going to be higher in the COD and BOD values, and to some extent, some suspended solids will also be present in it. So the treatment of these waste streams are very important before discharging into the surface water. So this is where the pollution control comes in picture in the distilleries industry. So now, here if you see the treatment schemes adapted for the distilleries include first the distillery wastewater are collected. It can be subjected to evaporation directly, or it can be coming to the biomethanation process. Okay. So in the case of evaporation, as I said, we have the multiple effect evaporator, which is going to completely remove the water from it, and then we can incinerate the solid residues also. Finally, we can recover potassium from it. So this is one of the way of treatment. And in the biomethanation based method, it can be a two-stage aerobic treatment. So in this one aerobic process, we are going to use the microorganisms like activated sludge process are all included. So the degradation of the organic contaminants will occur. So it can be helpful to reduce the BOD, COD content in the waste stream. Then after this secondary treatment, so aerobic treatment is a secondary treatment. So after this, we can go for the tertiary treatment for further purification, and then we can discharge the waste stream in the treated waste stream in the surface water. Or we can directly use after the secondary treatment with by skipping the tertiary treatment. So we can use this water for irrigation purposes, like a potable application. Instead of using it as a drinking water and discharging in the surface water, we can use it as the irrigation purpose. Okay. So now this is the treatment scheme adapted. So how this treatment is happening, we'll see in detail here. So MEE is the multiple effect evaporator. So in this evaporator, what happens? All the condensate and spent leaves are coming to the equalization tank. So in the equalization tank, it will be having a retention time of 6 hours so that the separation happens, and then it goes into the conditioning tank. So conditioning tank is mainly it uses the chemicals to bring the pH to a certain level, which ensures the further process will be okay for the waste stream. So the next process is ICX. So this is the anaerobic digestion channel. Okay. So what happens here is anaerobic digestion. So in the anaerobic digestion, we know what is the ultimate product. So the ultimate product is the biogas. So that gas is collected from the top as a gas holder and it is burnt in the flame. Okay. So anaerobic tank is here. So in this digester, digestion happens. Then the residual waste is again subjected to the aeration tank. So aeration tank again, as I said, is the activated sludge process, a kind of aeration. Secondary treatment happens, and then we have the secondary clarifier. So in the secondary clarifier, the settling of the sludge and the separation of the liquid stream is going to happen in the secondary clarifier. So here, one of the major input is the MEE. So multiple effect evaporator. This is going to bring on the condensate and spent leaves for the treatment. Okay. And then we have the second inlet, which is nothing but our cooling tower flow. We have two different cooling tower. One is the fermentation cooling tower and another one is the distillation cooling tower. So all the waste stream from these towers are directly coming here to the further advanced clarification step. So here the high rate clarification tank is there. So in this one, along with the solid and water, again it is getting treated. Okay. So after the high rate secondary clarification, we have the next filtration steps. So all these are filtration. Okay. After the advanced clarification process, we have multi-grade filter. MGF is the multi-grade filter, which composed of different layers. So after filtration in MGF, it is again subjected to ACF. So ACF here is the activated carbon-based filter. Okay. So again, the filtration is happening here. And then comes the UF. We know UF is the ultrafiltration. So we are reducing, first we are using the carbon and multi-grade components for filtering the solid particles, and then to increase the purity of the particular water, we are filtering it through ultrafilter. Okay, so ultrafiltration happens. Next comes the reverse osmosis. So by undergoing all these processes, now the water is completely clear water. Okay, and then finally they ensure its usage again. So we are using UV. So UV treatment is here. After this is a tertiary treatment. Okay. So after the UV treatment, we can reuse the water for the same plant, or we can check the conditions of it like POD, COD, and all the other water quality parameters. Then we can allow it to discharge in the surface water itself. Okay. This is what the process happening in the CPU. Okay. Condensate processing unit. So here, this is the P mentioned here as the diagram. So this wastewater is coming here, evaporated in the MEE, and then incinerated potassium recovery is happening. Then it can undergo biomethanation. So biomethanation is the process where it is happening. Okay. So equalization, conditioning, anaerobic digester, and biomethane is produced here. Then after biomethanation, it can go here for the two-stage aerobic treatment. Like we have the aerobic tank or like aeration tank, then the secondary clarifier, then the again second clarification using advanced clarifier. Then comes the different filtration steps and then the UV treatment. These are the tertiary step. Okay. This is the treatment scheme adapted in the CPU, condensate processing unit. So now this is about the pollution control in distilleries. Now we will move on to the pollution control in tannery. So coming to the lecture 47 about the tanneries. So in the tanneries, what is happening is tanning. So tanning is the process of treating the skins and hides of the animal to produce the leather. So whatever the shoes are made from the leather, and we have many jackets. So for every purpose and demand, we need the leather. To produce this leather, we are using the skins and hides of the animals. So generally, what happens in the earlier stages, tannin uses the natural tannin itself. So tannin is a acidic chemical compound which is used earlier. But nowadays, what we are using in the tanning process is the chromium salt. We are using the chromium salt. We know chromium is a toxic heavy metal. So the disposal of all the waste streams is very much important before we are discharging into the water, discharging the water stream, or before adapting the landfilling of sludge. We need to ensure that chromium content is reduced in it, and all other parameters are also very important to be predetermined before discharging into solid into the soil or into the water bodies. So now we will discuss the different steps involved in the tanning process, and what are all the compounds used for the production of the leather, and what could be the different waste streams produced from each and every steps of tanning process. Okay. So the first step is soaking. So this is to remove the dirt particles from the skins and hides of the animals. So they use the water, biocides, and enzymes. So in the soaking process, a lot of water is used. So the whatever the waste water produced will contain the total dissolved solid, suspended solid, and some amount of chlorides in it. Okay. The second step is liming. So liming, reliming, and unhairing. So we will be removing the hairs from it. So liming is going to happen. So this is mainly the flesh removal from the skins and hide. So for this we are using the sodium sulfate and limes. So this process will also release the wastewater which is rich in pH, BOD, COD. Again the suspended solid, and some amount of sulfur content will also be there because of the usage of sodium sulfide in it. Okay. So the next step is flushing. So this flushing can be a manual flushing or mechanical flushing. So this is to remove the flush. So we use a high amount of water in it. So this wastewater will also be rich in all these parameters. So again, finally, after these many process, we are going to delime our product. So deliming is nothing but removal of the lime so far we have used. Okay. So this deliming happens by using the salts called ammonium salts. Okay. So ammonium salts are used to delime, like to remove the lime from our skins and hides of animals. And whenever we are using the ammonium salt, we will be having the same in our wastewater stream. So in here we also use an enzyme called batting enzyme. So this is to soften the material before producing the leather. Okay. So now the next step is pickling, where again we use the water, biocides, and enzyme. So the wastewater stream now will have the low pH in it because we have again neutralized it, and then we have some amount of chloride and sulfide in it. Next is the important step where we are doing the chrome tanning. So for this chrome tanning, we use the salt chromium. Okay, that is very important. So we use the salt chromium. This is a very important step. We use chromium, sodium salt, and some vegetable tannins, okay, for the conversion of these skins and hides into leather. So in this one, we will be having chromium, TDS, sulfate, chloride, vegetable tannin content will be somewhat higher in the wastewater stream of this process. So after this chrome tanning, the splitting, shaving, trimming. So it is we are trying to bring our leather in shape. Okay, for that we are doing all these steps. So whatever the waste produced will also be again left into the waste stream. So here chroming and syntons are used for again re-chroming and re-tanning to ensure the complete conversion of the leather process. And now then we use the water, dyes, and flat liquor. So why we use the water dyes and fat liquor here means, so in the dyeing and fat liquoring, the tensile strength of the leather is getting increased. Okay. Finally, we are drying our product and the finished leather is the end product of dye. So if you have seen here, we use a lot of water in this process. So tanning is also water intensive process. So whatever the wastewater stream produced is classified into two types, which is the chrome and non-chrome water stream. So what is chrome and non-chrome water stream? So here it is the chrome tanning. So in the chrome tanning only we are using the chromium. Okay. From this step only we are going to have the chromium content in our wastewater. So after this we will be having the chromium content. Before this, we don't have any chromium in the process. So those are all classified into non-chrome. And where the chromium comes into picture, those what wastewater stream are classified as the chrome stream. So why this is classified means because treating a lot of water, combining all the waste stream into a single stream and treating the chromium and recovery of chromium is very much difficult. So there are two water streams in these industries, tanning industries, and these are treated in different ways. So if you see this process flow chart, before going to the ETP, how these chromium is recovered is explained here. Okay. So this is the chrome recovery section. So first, what is happening means from the processing unit, from the tanning unit, we are collecting the waste, which is the chrome bearing waste. Okay, it is collected and equalized, and then it goes to the chrome treatment tank. The first step is it is going to the treatment tank, and the second step is it is coming to the recovery tank. Once the chrome is treated, it is coming to the recovery tank. So in the recovery tank, what happens? All the chromium are all removed. Okay. So chromium is removed and it is again going to the, after the removal of chromium, it is going to the non-chrome waste stream. So now the chrome waste stream is treated, and after removal of chromium, it is mixed with the non-chrome waste stream. So the flash mixture is used for mixing both the non-chrome waste stream, and then it is going for the ETP section, which is having the primary clarifier. So the primary clarifier separates the sludge and the top water. So it is going to the secondary process called aeration tank. So here the activated sludge process happen. So our solid particles will form the flocks and all the sludge will be settled down in the secondary clarifier. So whatever sludge is produced at the bottom is collected to the sludge drying bed, and the clear water is going to the treated water collection tank. Okay, this is what happening in the tanning wastewater treatment process. So the effluent treatment process include the primary clarifier, aeration tank, secondary clarifier, then the treated water is collected. Okay, so now coming to this chrome recovery section. As I have discussed, chrome and non-chrome are the two waste streams. Once the chromium is removed, this chrome stream is again fed into the non-chrome stream. But how this chromium is recovered is what given here in this flow chart. Okay, we use some chemicals, mainly the magnesium oxide, MgO, okay, and then we use the sulfuric acid, H2SO4. So these two are the major components included in our chrome recovery section. So first, what is happening is in the chrome treatment tank, we are adding the MgO, okay, in a particular dosage. For this much volume of the chrome waste stream, this much kg of MgO is added. Like that, there is a ratio. Okay. The main aim of this chrome treatment tank is to bring the pH to 11.5 to 12. Like the pH should be above 11.5. That is the condition. So it is residing here. What is happening here is once the chrome waste stream is mixed with the MgO, it is going to form the chromium oxide. Okay. So it is going to form the chromium oxide. So this chromium hydroxide. So this chromium hydroxide is formed here, and then this is subjected to this chromium hydroxide containing slurry is subjected to the chrome recovery tank. Once treatment is done, it is coming to the recovery tank where it is treated with the H2SO4. So with the MgO, water, and the chromium in it, it's going to form the chromium. chromium oxide and magnesium sulfate. And then this chromium hydroxide containing slurry is passed to the recovery tank. So with the chromium hydroxide, H2SO4 is getting reacted. Finally, what is the product going to form is chromium sulfate. Cr2SO4 thrice. Okay. So this is the end product going to form, and this is what recover. So we are going to recover the chromium in the form of chromium sulfate. Okay, this is the precursor for the chromium salt. Okay, so this chromium sulfate is now recovered. Then again, after this treatment, like after the removal of the chromium sulfate, this chrome stream is mixed with the non-chrome waste stream. Okay. This is what in detail happening in this chrome treatment and chrome recovery section. So mainly a lot of wastewater are produced in the tanning industry. From each step, we can observe the different kind of pollutants being added to the water used. So we are dividing the streams into chrome and non-chrome, and we are recovering the chromium from it, and then the non-chrome wastewater is finally treated together, and this sludge after the chromium removal can be landfilled. But with the chromium, we cannot landfill the sludge because these chromium, because of the landfilling of these sludge, can get accumulated in the groundwater stream, and it have the high chance of getting contaminated in the groundwater table. Okay. So now coming to the lecture 48, this is dealing about the petroleum refinery and petrochemical industry. So what is the difference between the petroleum refinery and petrochemical industry mean? So here petroleum based product are formed in the petroleum refinery, and from the petroleum based product we are forming some chemical products, okay, by using the petroleum product. That is the petrochemical industry. So we will look in detail about the petroleum refinery first. So what is the feedstock? What is the major precursor of this petroleum refinery means crude oil. Okay. So this crude oil is first obtained and it is subjected to distillation. So in this atmospheric distillation, so the distillation will have different traits, right? So what is the major principle behind the distillation? Based upon the difference in the boiling point, the mixture of liquids are separated. Okay, that is the principle behind the distillation column. So at different boiling points, different products are removed. So in the atmospheric distillation of crude oil, light naphtha, heavy naphtha, and then jet fuel, kerosene, diesel oil, and atmospheric gas oil. So these many products are removed from the mixture of liquid crude oil due to the difference in the boiling point. Okay, we will see one by one. So now whatever is given in this color, blue color, or the end product obtained from it. Okay, so these are all the finished product. So it has different units, and we will see it one by one. So first, if you take the first output, light naphtha, it is subjected to the hydro-treated. So hydro-treated, it is nothing but it uses the hydrogen. So it uses the hydrogen gas to remove the sulfur from the naphtha molecules. Okay. So from the naphtha, sulfur is removed, and then this treated light naphtha is subjected to the isomerization plant. So the isomerate is the product obtained from it. Now coming to heavy naphtha, it is again hydrotreated. The sulfur particles are removed from it, and then it is undergoing the catalytic reform. So reformation happened, like the octane rings increased, and so this reformate is collected at the end. Next is the jet fuel kerosene. It is going to the Mirox treated. So again the sulfur is removed here. Finally, this jet fuel or kerosene is the end product obtained from this stream. Now the diesel oil is there. So again the sulfur is removed by the help of hydrogen as hydrogen sulfide. So the diesel oil is another end product. Okay. Now coming to the bottom product, from the bottom, whatever the components obtained from the bottom are going for the secondary distillation, nothing but vacuum distillation. So in the vacuum distillation, so the pressure is going to be below the atmospheric pressure to separate the particle. And here, the light vacuum and the heavy vacuum gas oils are produced. So what happens here is light vacuum and heavy vacuum gas oils are produced. This again hydro-treated to remove the sulfur, and finally all these products are going for the next stage of treatment process like alkylation. So in this alkylation, what happens? The end product alkylate is obtained. So this alkylate is formed by alkylation of butane, butene, and pentene. Okay, by alkylation of these things, we are going to obtain the alkylate. And then here we have the fuel catalytic cracker. So in this one, again, naphtha formed is treated using the hydrogen and the sulfur compounds are removed. And this FCC gasoline is obtained. So whatever the subproducts obtained were pulled together to obtain the gasoline blending pool. Okay, it is taken to the gasoline blending pool. This is the final product here, finished product. So now coming to another category. So here the FCC gas oil is can also be obtained as the fuel oil, the another product. And we have the coke unit. So in this coker unit, what is happening is this is fed from the bottom product of the vacuum distillation. So one subunit is taken to the coker unit, and again here the petroleum cokes are formed from this one. This is the another finished product here. So now the another one is the asphalt blowing. So asphalt is formed from the bottom product of as the bottom product of the vacuum distillation. Okay. So this is about the intermediate product and the bottom product. Now coming to the top product, from the top, the gas molecules are collected and the gases are processed and Mirox treated as they. So finally, the gaseous products are collected here as LPG, okay, liquefied petroleum gas and butanes are obtained as the finished product. And then the fuel gas is undergoing the amine treatment. So here the amine treatment is happening and refinery fuels are obtained, and all the H2S is removed and it is passed to the sulfur treatment plant. So where stripping happens. So after the stripping, we can obtain the sulfur from the H2S. Okay, these are all the different products obtained from the crude oil in the petroleum refinery. Okay, from the products obtained in the petroleum industry, we can some other useful chemical compounds, useful products can also be formed. Okay, that is what happening in the petrochemical industry. So mainly this naphtha, which is olefins and aromatics, are all can be used for production of these useful chemical products. Okay, so now ethylene, propylene, butadiene, benzene, xylene, these are all the different building blocks for the chemical formation, which undergoes the various processes. We can read it one by one. But finally, what products are formed from the intermediate product? These are all the intermediate product. Okay, these are all the building blocks, and these are all the intermediate products. So from these intermediate only, the final products like dyes, and then the pharmaceutical product, then some kind of detergent, plasticizers, and then polyesters, acrylic fiber, glycols, ethers. So these are all the some of the chemical product, which are all the useful product obtained from the petroleum based product. Okay. So these petroleum based products are obtained from the crude oil, and these chemical products are obtained from the petroleum based product. Okay. So this is what happening in the petroleum refinery and petrochemical industry. Now, what are the different kind of pollution we can expect? We can expect from these industries means mainly we use lot of stripping of sulfur, right? So a lot of sulfur is removed in the gaseous form from each and every stage. So the SOx and NOx emission is the highest probability of pollution from these kind of industries. And whatever the products formed here will also have some volatile organic compounds. So those volatile organic compounds are also another form of pollution. So these are the different pollutants from the different stages we have to keep in mind before releasing them into the atmospheric air. Okay. So now coming to lecture 49, it is also dealing about the pollution control in different industries. So the first one is the pulp and paper industry. So this is the industry where the paper is produced. Again, we know that paper production mainly uses the wood as the source. Okay, major portion is wood. Wood is the feedstock for the paper production, and it is also a very water intensive process. So first we can collect the different wood blocks, and those logs are debarked, and then these are chipped into smaller size. With the help of mechanical pulping or chemical pulping, we can extract the pulp, and here the bleaching is happening to increase the color, and then the pulp blending is happening. Then we are going to add some other additives, okay, to form the paper. So once these additives are added, the paper formation is started. Then coating of the material is happening. Then finally calendar is happening to bring into a particular shape. Finally, the end product paper is produced. So if you see this one, what are the different waste stream produced from this pulp and paper industry means? We use a lot of water in this one, right? Each and every step involves water for the formation of paper. So this wastewater is collected, and after the primary treatment, nothing but sedimentation and clarification. After the primary treatment, it is subjected to the anaerobic digestion. Okay, because of solid waste is present in a higher amount. So this anaerobic digestion will be helpful to produce the biogas and methane. And then this after the anaerobic digestion, we can subject it to the aerobic secondary treatment. Why we are always following the anaerobic digestion followed by the aerobic treatment means it will be having the good efficiency. Once it is aerated, we cannot go for the anaerobic digestion. So it always follows this order. First is the anaerobic digestion, next is the aerobic treatment. Then comes the secondary sludge from it. So we can evaporate and incinerate. Finally, the sludge can be landfill. And then after the secondary treatment, the clear water can be used for the irrigation purpose, or else we can further process it by using the tertiary treatment method like UV treatment, different kind of filtration, photocatalytic oxidation. So all this tertiary treatment can be involved, and these water can be subjected to the surface water. Okay, so mainly here we have to check the BOD and COD content in it. That is the major contaminant. That is the major water quality going to be affected because of the pulp and paper industry. Okay. So now coming to the fertilizer industry, we know that fertilizer is now inevitable for the crop production. Like our soil fertility is getting decreased, so we are in need of fertilizers to improve the soil fertility and to maximize the yield of different crops. So the mainly used fertilizer which is inevitable in our agriculture is NPK. So the major source of N is coming from urea, and then the phosphorus, the main source is the single superphosphate, it's a fertilizer. We also have triple superphosphate and many the different kind of phosphate, but SSP is most common. And then potassium is produced from muriate of potash, and we also have diammonium phosphate, monoammonium phosphate. These are all different sources of nitrogen and phosphate. So we are going to see the urea, SSP and DAP production process as an example for the fertilizer industry now. So how this urea is produced means urea is produced. This is the chemical formula of urea. Okay, so this urea is produced by the reaction between the ammonia and carbon dioxide in a reactor. So after this, the stripping is going to happen, then evaporation is there, drilling and bagging. So if you look into each and every step, the waste produced from each and every step is given in the flow diagram itself. So here in the stripping and decomposition, there is a lot of spillage and leakage. And then here in the evaporation, vacuum condensate is released. And in the prilling process, when you are producing the urea as granules and all, the spillage is going to happen. And then we are going for bagging of urea. And before this also, a lot of dust particles are released. So this is how the air is polluted. And then this is about the leakage of the condensate and the spilling of urea. These are all going into the water stream, going to affect the water quality also. So in the preparation of SSP also, if you see, it uses a rock phosphate. Okay, it is obtained from the earth only. So this rock phosphate is mixed with the water and sulfuric acid, and then finally the SSP is formed. So for this one, again, when it is mixed with the water, lot of water is going to be contaminated. Here mainly it deals about the uh, air pollution. Here it is mainly majorly affecting the water. Okay, so water is highly contaminated here. And here in between we have a scrubber unit. So scrubbing is going to happen. So in the scrubber unit and all, we can expect the gaseous pollutant from it. And in the curing shed also, you can expect a gaseous pollutant from the production of SSP. And again, the same is applicable to the DAP process. So for this, what is the reactant used is the phosphoric acid and ammonia. So these two are getting reacted to form the DAP. In between these processes are there. So we can expect the air pollutant by emission from the scrubber. And here from the de-dusting unit, you can expect the dust particles in it. Okay. So all these dust particles should be captured in the ESP, and these should be precipitated down, should be captured, and then the fresh uh, when before releasing into the fresh air, these contaminants should be removed. That is the very important one in the fertilizer industry pollution control. So the last industry we are going to discuss about is the pollution control in copper smelting industry. So this copper smelting industry mainly uses the different ores. Okay, so different ores are used in this copper smelting industry. So how this copper production happens is given in this figure. So this blue line is indicating the product flow, different product formation, and this black line is indicating how the pollution flow is happening from each and every step. So in the first step, after the extraction of the ores, if you see, there are two different type of ores, right? Sulfide ores and oxide ores. So in the case of oxide ores, we can directly extract the copper from it. Okay. So oxide ores will have less amount of contaminant. But in the case of sulfide ores, a lot of sulfur content will be there along with the copper itself. So removal of sulfur is uh, very difficult thing in this one. So what we are adapting is first we are concentrating this ore. So for concentration, we are using the flotation step, and then the melting is going to happen. So in the electrostatic precipitated chamber, what is happening is with the help of electrical current, the sulfur content is removed. Okay. So now the sulfur content removed is going to the sulfuric acid plant, and this can be used for production of sulfuric acid. And after the conversion of the sulfide ore into blister copper, this is easily refined to produce the refined copper. This is how the copper is produced. So in the case of oxide ore, less amount of contamination is there. In the case of sulfide ore, it is a very laborious process to produce the copper, because the major contaminant is the sulfur content in it. So, so here if you see, the main pollution is into the atmosphere. So mainly it is going to pollute the air. So we have to be sure we have to capture all the volatile organic compound from the ores, and during this process, smelting process, we have to be very careful in capturing all the gaseous component before releasing into the air. So now coming to some sample questions for this week 10. First question is, which of the following feedstock contributes to the largest production of ethanol globally? So we have discussed a lot of sources for ethanol production. In case of India, it is molasses, but they are asking the global production. So the right answer is coarse grain. Okay. Next question is percentage of composition of fermentable sugar matter in the molasses. So molasses is obtained from the sugar industry. How much amount of fermentable sugar is there in it? It is 40 to 45 percentage. Okay. Next, the dilute molasses media present in the yeast vessel is heated at the temperature of. So during the fermentation process, we use the microorganism called yeast for its enzyme. And initially the molasses is diluted and then only it is mixed with the yeast before fermentation process. So what is the temperature maintained they are asking? So the temperature maintained is 85 to 90 degrees Celsius. It ensures the conversion of the disaccharide into ethanol. Okay. Next is favorable condition for the Maillard reaction. So what is the favorable condition in this one? It is again the temperature should be greater than 50 degrees Celsius and pH should be 4 to 7 to ensure the product formation. Okay. So now the next question is tanning is the process of treating the animal skin and hides to produce. So tanning, it is an industry. It treats the animal skin and hide to produce the leather. Okay, leather is the final product. Sludge generated during the tannery process is generally managed by. So from the tannery process, we are obtaining a sludge. So how this one is mainly managed? Okay, generally managed. They are asking. As I said, a lot of water streams are produced, wastewater streams are produced from tannery sludge, and mainly it is going to contain chromium in it. Okay, so whenever chromium is there, after ensuring the complete treatment only, it can be landfill. So landfilling is mostly not suggested before ensuring the proper treatment. So what is the best method they are adapting to eliminate the sludge generated in this process is landfilling only, and then less amount is incineration. But the main thing is after the chromium removal only, it is landfill. Okay. So we have seen. So why this is emphasized again and again is because of the higher amount of usage of the chromium sulfate in it. So once the chromium sulfate is recovered from the chrome storage, recovered to the chrome storage tank, so this water is mixed with the non-chrome waste collection tank. So whatever sludge obtained here, it can be landfilled after ensuring that chromium content is not there. Okay. And then the next question is, which of the following is not produced during the processing of crude oil? We have seen that we have a distillation column and the crude oil is fed into it. So once this crude oil is fed into it, we are producing the different product based upon the difference in the boiling point. We are obtaining different product like gasoline pool, and then LPG gases, then diesels, fuels, and but not the bio oil. Bio oil cannot be produced from the crude oil. Okay. Now the next question is wastewater generated from the chemical fertilizer industry. So chemical fertilizer industry mainly contain. It contains everything. It contains the alcohol, contains ammonia, it contains heavy metals. So all of the contaminants are present in the wastewater produced from the chemical fertilizer industry. Wastewater generated in copper smelter contains. So copper smelter also contain all of the above. All the soluble metal compound, non-soluble metal compound, oils are all produced in the copper smelter industry. So now coming to the problematic question, the last question for the sample questions of week 10 is in an industrial biogas plant. So in an industrial biogas plant, food waste is anaerobically digested. So it is a biogas plant. So in this one, all the food waste collected or anaerobically digested to produce the biogas. The slurry contains 10% of solid food grains. The elemental composition of food grains on a dry basis is C. Carbon is 50%, hydrogen is 5%, oxygen is 35%, and nitrogen is 10%. So if we add this one, 50, 55, 60, 90, 100. So it is 100% based on the mass. Okay. Now, around 90% of the food grains are converted to biogas, and all the converted hydrogen forms the methane. So, 90% of the food grains are converted to biogas, and one key word given is whatever the hydrogen uh, is present in this biogas is produced as the methane they are telling. So absolutely we have two biogases. One is the carbon dioxide, another one is methane. So whatever the hydrogen present here in the food grain is completely converted into methane. If the flow rate of the slurry is 3,500 liters per day, so this is the flow rate. Calculate the rate of biogas production. How much biogas is produced? That is the question. So it is going to use the stoichiometric balance to find the biogas amount. The right answer is 467.25 kg. We will look into the solution now. So first we will write the data given. Initially it is given like in a biogas plant. The input of the slurry is 3,500 liters per day. So the flow rate is 3,500 liters. And another thing mentioned is the slurry contain only 10% of solid food grain. So solid food grain in it is only 10%. First we need to find the dry solid food grains used for the production of biogas. It is 3,500 into 10%, which is 0.1. So it is 350 liter. It is written as 350 kg by assuming the density as 1 kg per liter. Okay. So whatever in liter is written as kgs since the density is assumed as 1 kg per liter. Now we know that CHON composition, right? The CHON composition is given as 50 percentage and 5 percentage, 35 percentage and 10 percentage. Okay. So now with this composition, we know that 350 kg is the amount of food grain present in the slurry. Okay, this food grain only contains the CHON component, and this is used for production of CO2 and CH4. Now calculate the amount of CHON in terms of kg in the 350 kg of food grains just by multiplying the respective mass percentage with 350. Okay. Now amount of C present is 350 into 0.5, 175 kg. Amount of H present is 350 into 0.05. Since it is 5%, it is 0.05, which is 17.5 kg. And amount of oxygen present in 350 kg dry food grain is 350 into 0.35 since it is 35%. So 350 into 0.35 is 122.5 kg. Now amount of nitrogen present in 350 kg is 350 into zero point 0.1 since it is 10%. So it is 35 kg. Now we know the mass of CHON for the 350 kg of solid food grains in the slurry. Now, another data given is around 90% of the grains are converted to gas. So, only 90% is converted to biogas. It is not 100% efficient. So, remaining 10% is going to be there as the food grain itself. 90% is converted. For the production of the biogas, CO2 and CH4, what are all used is carbon, oxygen, and hydrogen. So in this one, so amount of C converted. Okay, so oxygen is there, hydrogen is there, carbon is there. First, we are choosing the amount of carbon. So amount of carbon converted to biogas. So 175 kg of carbon is there in our food grain, and 90% is converted to biogas. So multiply it with 0.9. So amount of carbon converted is 157.5 kg. Now, Hydrogen converted to biogas is 90%. Again, 90% is converted to biogas. So out of 17.5 kg of hydrogen in the food grain, zero point 0.9 into 17.5 is 15.75 kg is there converted to biogas. And all of the hydrogen produced, like converted to biogas, is converted to methane only. It is what given in our question. So all of our hydrogen produced as biogas is converted in the form of methane. So we have to use the stoichiometric balance to find the amount of methane. Okay. So in this equation, for 1 mole of methane, okay. So 1 mole of methane. 1 mole of sorry, 4 moles of hydrogen is required. We require the 4 hydrogen atoms, right? So, so in the CH4, there are 4 hydrogen atoms. That is what I mean. 4 hydrogen atoms are there. So the molecular weight of hydrogen is 4 into 1 is 4. The molecular weight of CH4 is 12 plus 4 is 16. So 16 gram of CH4 is formed from 4 grams of hydrogen. That is what I'm coming to explain. So the methane production can be calculated by dividing the 16 by 4 into 15.75, which is 63 kg. Now we know the amount of hydrogen used for this methane production and the amount of methane produced from the hydrogen by calculating the amount of hydrogen, okay, in the biogas. So now finally we have to calculate the amount of carbon used. If you see, the hydrogen is fully converted into methane only, but in the case of carbon it is not like that. Carbon is going to form two type of biogas product. One is the carbon dioxide and another one is the methane. So first we need to know, out of the 90% converted into biogas, that is 157.5 kg, how much carbon is converted as CO2 and how much carbon is converted as methane. Now with the help of hydrogen, we have found the amount of methane. So in this methane, how much carbon is there, we can easily calculate. As we have calculated that 4 grams of hydrogen is required for 16 gram of methane, like same way we have to calculate for carbon also. So 12 gram of carbon is required to form the 16 gram of methane, right? So divide the 12 with 16 and multiply it with 63, which is the total methane. So in the total methane, how much amount of carbon is required? For 63 kg, how much carbon is required? 47.25 kg. Okay. Now we have found that out of 157.5 kg of biogas, uh, like a carbon converted to biogas, 47.25 kg is required only for methane production. So how much is required for CO2 production? We can subtract and find it, which is nothing but 110.25 kg. So now we know how much CO2 is produced. Carbon is used for CO2 production. We have to find the amount of carbon dioxide produced with the help of the C. Same stoichiometric balance is used. So CO2, the molecular weight is 44. For the production of 44 grams of CO2, we require the 12 gram of carbon. Okay, one carbon is there in the carbon dioxide. So just multiply the 110.25 into 44 by 12 and find for this much amount of carbon, how much amount of carbon dioxide can be formed, which is nothing but 404.25 kg. Now you have to add both the methane and the carbon dioxide because these are all the biogas. That is what asked in the question, how much amount is produced. So add the CH4 and carbon dioxide, 63 kg of methane plus 404.25 kg of carbon dioxide are produced. So totally the biogas produced is 467.25. Okay, I hope it is clear. If not, we have the another problem, same kind of problem. It will be clear in that. Shall I move on? We can discuss the tutorial problem. Do you have any doubt? Okay.
Ma'am, explain methane production once again.
Methane production.
Methane. Yeah.
Okay. So here, I think till this step it is clear. We'll explain. So now if you see, we know the amount of carbon, hydrogen, oxygen and nitrogen content in the food grain and 90% is converted to biogas. So we know out of this much carbon and hydrogen, how much amount is used for biogas. We have calculated those two. Now, in this one, whatever the hydrogen converted to biogas, that this 15.75 kg is entirely is used for production of methane. Okay, so if you take the methane CH4 to form 16 gram of methane, it is the molecular weight of methane. To form 16 gram of methane, we require the 4 grams of hydrogen, right? We need 4 grams of hydrogen. 4 hydrogen is there in 1 methane molecule, right? So, for 4 grams of hydrogen, 16 gram of methane is formed. In a similar way, for 15.75 kilogram of hydrogen, how much amount of methane can be formed? It is a direct question. Okay, that is why we are multiplying 16 into 15.75 divided by 4. Okay, for 4, this is in same unit. For 4 grams, 16 grams is formed. For 15.75 kg hydrogen, how much kg is going to be formed? That is the question. Okay. Now with this, we found the methane produced as 63 kg. Now we need to calculate the amount of carbon used for the methane production. With the help of same stoichiometric balance, 12 gram of carbon is required to form 16 gram of methane. Okay, 12 grams is required for 16 gram of methane. So now you need to find for 63 kg of methane, how much amount of carbon is consumed. That is why 63 into 12 divided by 60, which is nothing but 47.25. This much kg is used for methane production. Subtracted from the total amount of carbon converted to find how much grams of carbon is used for CO2 production. Okay, is it clear now?
Yes, ma'am. Now clear.
Okay.
Yes.
We have the same problem with different data again. So now I hope it will be more clear to you. So the first question in tutorial, this is tutorial 10, right? Mistakenly. Tutorial 10 is in an industrial biogas plant, food waste is anaerobically digested to produce biogas. The slurry contains 10% of solid food grain. This is same. This data is same. 10% of solid food grain. And the total elemental composition is different. Carbon is 52%, hydrogen is 9%, oxygen is 29, nitrogen is 10, and all of them are given in mass percentage. Okay, if we add this, it should be 100. And then around 85% of the waste is are converted to biogas. 15% is left out as food grain itself. Now all the converted hydrogen forms the methane. If the flow rate of the slurry is 4000 liter per day, calculate the rate of biogas production. Okay. So now the flow rate is given as 4000 liter per day. Assuming that the density of slurry is 1 kg per liter, we can find the dry solid waste of food grain in kgs. 4000 liter is there and only 10% is food grain. So multiply 4000 into 0.1. So 400 liters. So assuming the density as 1 kg per liter, it is taken as 400 kg. Now, in this 400 kg, how much kg of hydrogen, how much kg of carbon, nitrogen, and oxygen are present is calculated. Since we know the mass percentage, of the CHON. Just multiply the 400 into the respective mass percentage to obtain the mass of carbon, hydrogen, oxygen present in this 400 kg of dry grain. Okay, so these are all the this much kg of carbon, hydrogen, oxygen, and nitrogen is present in our food grain. Now, we are going to find the amount converted to biogas. The efficiency of conversion is given here as 85%. Okay, so 100 percentage is 208 kg. Okay, in this one only 85 percentage is the carbon converted into biogas. So multiply it with 0.85, we will obtain 176.8 kg. Then amount of hydrogen converted to biogas is 100 percentage is 36. So 85 percentage is 30.6 kg. So this is the data we are going to use for the calculation of amount of biogas. So carbon is 176.8, hydrogen is 30.6. Now we know that CH4 contains 4 molecules of hydrogen. So for 16 grams of this methane, 4 grams of hydrogen is required. And for 30.6 kilogram of hydrogen, how much amount of methane can be formed? Okay, the same calculation. So 16 by 4 into 30.6 will give 122.4 kg. So here it is given as rate of biogas production only. Unit is not given, but in the solution two units are given. One is in terms of kilogram and another one is in terms of kilomoles. Okay. So 16 by 4 into 30.6 kg is 122.4 kg. So we know the molecular weight of methane. If you divide the weight with the molecular weight 16, you will obtain 7.65 kilomoles. Okay. Next is the calculation of carbon used for methane production. So it is important to find the amount of CO2 produced. So we again know that 12 grams of carbon is required for production of 16 gram of methane. Okay, so 12 grams is required for 16 gram of methane. So 12 by 16 for 122.4 gram of methane produced, how much carbon is used? So multiply it with 122.4. It will give you 91.8 kilogram. So subtract this 91.8 kg which is used for methane production from total amount of carbon converted to biogas 176.8 to obtain the C used for CO2 production, which is nothing but 85 kg. So 85 kg of carbon is used for CO2 production and 91.8 kg of carbon is used for methane production. With the help of the carbon content, now we can easily find the amount of CO2 produced. Like I said, for the 42 grams of CO2, 44 grams of CO2 production, 12 grams of carbon is required. Okay. So with the help of 12 grams of carbon, 44 grams of carbon dioxide is produced. So with the help of 85 kg of carbon, how much amount of carbon dioxide is produced? So 85 into 44 by 12 is equal to 311.66 kg. This is the amount of CO2 produced. So divided with 44, then we will obtain 7.08 kilomoles. Okay. Now we can find the total amount of biogas produced by adding the 91.8 uh, sorry by adding the 122.4 and 311.66. The total amount is 434.06 kg. This is the amount of biogas produced in this anaerobic digester. So now you can obtain the same in kilomoles by dividing the individual amount with their respective molecular weight. Okay. We divide 122.4 by 16 and 311.66 by 44 and add these two. We will obtain this 7.65, 7.08, total 14.73 kilograms. Okay. I hope this question is clear. Now the next question is, it is based on the CP, distillery unit based question. Okay. It is a lengthy question, but very easy problem. It has a lot of assumptions in it. We will see this step by step. So a distillery unit producing 180 ppd alcohol. So this is the alcohol producing distillery unit. So it generates 42.93 meter cube MEE condensate. So the condensate flow rate is 42.9 meter cube per hour and 3.75 meter cube cooling tower flow rate. So two different streams are there. Condensate stream flow rate is 42.9 meter cube per hour. And the cooling tower blowdown flow rate is 3.75 meter cube per hour. Determine the critical dimension of the secondary clarifier. So this is the first question. Determine the dimension of the secondary clarifier. And then multi-grade carbon filter. So this is 1A and this is 1B. So we need to find the dimensions of the secondary clarifier and multigrade and carbon filter. Also determine the oxygen requirement. So this is the second question. So how much amount of oxygen is required in the aeration tank? Assuming the inlet BOD of the aeration tank is 130 ppm, aeration is done by using the diffuser and the hydraulic retention time and surface loading rate for the secondary clarifier are given as 5 hours and less than 18 meter per day. So this is the data given and then the HRT of the filter unit for the secondary clarifier data is given and for the filter unit the HRT is 6 minutes and the length to diameter ratio is given as 0.8. Okay, with this data, in the first one, we need to calculate the dimensions. Okay, first question is to calculate the dimension of different unit process. So first one is the SC, secondary clarifier. Second one is the filter. What are the different filter? NGF and then carbon filter also. So ACF, activated carbon. So this is the first part of the question. Second part is to find the amount of O2 required. Okay, this is the question. Now we have discussed the process flow diagram of the condenser unit. So condensate unit we have discussed already. I will explain it once again. It will be easy to solve the problem. As the question has mentioned, this is a distillery unit. So in the distillery unit, it is going to produce the alcohol of 180 TPD. For this, it is going to generate two waste streams. So the first waste stream is the condensate waste stream. The flow rate of the MEE condensate, which is multiple effect evaporator, is 42.9 meter cube per hour. So the first stream flow rate is given as 42.9 meter cube per hour. And it is going to the equalization tank, conditioning tank, and then the aerobic digestion is happening. Anaerobic digestion is happening, and biogas is produced here. Okay, and then it is coming to the aeration tank. So in this aeration tank, we are using the diffuser. Okay, we are using the diffuser, and we are sparging the air here. So how much amount of O2 required? This we need to calculate. Okay. Now after this aeration is going to the secondary clarifier. So this secondary clarifier dimensions are required to be calculated. So this dimension is required to calculate and the hydraulic retention time is given as 5 hours and then the surface loading rate is how much loading is done in the secondary clarifier means 18 meter per day. If you see the height in the secondary clarifier per day, it can go up to 18 meter. That is the loading rate in the secondary clarifier. This dimension is to be calculated. Then comes the secondary waste stream, cooling tower flow down. The flow rate of this stream is given as 3.75. You can write down here. So it is 3.75 meter cube per hour. And then after mixing of these exit stream and this inlet stream, it is coming to again to the clarification tank. So here high rate solid clarification tank is there. After that we have different filters, just NGF multigrade filter, then activated carbon filter, ultra filter, reverse osmosis, then UV treatment, finally reusing in the plant. So here they are asking us to find the dimensions of these two filters. Okay, For this one, they have given us the data of HRT of the filter unit. So how much time it is residing here means 6 minutes is the residing time, residence time. Okay. And then what is the dimension ratio given here means L by D is given as 0.8. I hope the question is clear. We need to find the dimension of SC and then ACF MGF, and then we need to find the amount of O2 used in the aeration tank, and where the inlet BOD is assumed to be 130 ppm. Okay, and other data are given to solve the question. So I will read this one before solving it. In distillery ETP, MEE condensate is treated through the condensate polishing unit, through the equalization tank, anaerobic digester, aerobic tank, followed by the tertiary treatment. However, the cooling tower flow down is treated only through the tertiary unit. Thus, if we assume that there is no loss of water during the process and ignore the sludge volume, only the condensate water will be processed in the secondary clarifier. However, both condensate and blow-down water will be used in a multigrade or carbon filter. That is what I have explained so far. So, to calculate the dimension of the secondary clarifier, we can account only one waste stream, which is nothing but the condensate, because the cooling tower blowdown is coming after the secondary clarifier only. So, we can take the data of the condensate alone to find the dimension of secondary clarifier. So we know the hydraulic retention time of the secondary clarifier, which is 5 hours, and the working volume of the secondary clarifier will be. So we know the flow rate. Flow rate is given as 42.9 meter cube per hour. And how much time the water is settled down here means 5 hours. So for every hour, 42.9 meter cube of water is passed into the SC. So 5 hours means, so just multiply 5 into 42.9, which is nothing but 214.5 kiloliters of water will be there. And then comes the surface loading rate. We know that surface loading is 18 meter per day. So in a day, 18 meter it is loaded. So it can be again meter per day is written as meter cube per meter square day. This is the actual unit. After cancelling only, it will be coming as meter per day. Okay. So now what they are doing is they are converting it to hour. So in a day, 24 hours are there. So 18 divided by 24. So 18 by 24 will give you 0.75 meter cube per meter square hour. It is nothing but 0.75 meter per hour. Okay. So the cross section area of the tank will be. So what is the cross section area? So to cross section area is given in meter square. To find something in meter square, what we have to do is we have to divide the meter cube per hour by meter per hour to obtain the cross-sectional area meter square. These are all simple unit-based solving. Okay, so 42.9 is the flow rate divided by 0.75 is the surface loading rate. Divide them, which is nothing but 57.2 meter square. This is the cross-sectional area. Now we have to find the height of the clarifier. So this is the clarification tank. So the sludge will be there, clear water will be here. Okay, so we are going to find the height of the secondary clarifier with the volume given. Okay, so now the total capacity of water filled in that 5 hours is up to this height, right? This much height, the water is filled for 5 hours. That is obtained by dividing the 214.5 with 57.2, which gives you the height, which is nothing but 3.75. But how this height is calculated means this height is calculated with the help of the loading capacity of the secondary clarifier. But to obtain the actual dimension of the secondary clarifier, it can be written as capital H. Okay, to obtain this, we need to consider this one. So this condition is considered that at least 0.3 meter free fall is necessary. Thus, the actual height of the secondary clarifier is 3.75 plus 0.5, that is 4.0. Like in the secondary clarifier, you cannot entirely fill the clarifier with the wastewater. Around 0.3 meter overhead space is required. It is the basic condition. So whatever the height we have obtained with the help of the loading capacity, just add the 0.3 meter to it. We will obtain the actual height capital H as 4.05 meter. Okay. Now to calculate the actual volume of this entire secondary clarifier. Okay. To calculate the actual volume, just multiply this height with the cross sectional area. Okay. So cross sectional area will not vary. So cross sectional area is same around the all over tank. So just multiply the 57.2 meter square into 4.05 height to obtain the actual volume, which is nothing but 231.7 meter cube. Now we have obtained the total volume. So easily we can obtain the radius. Okay. So the radius is obtained by volume is equal to uh, so the radius of the secondary clarifier will be square root of 57.2 divided by 3.4. So where this 57.2 is coming from means this is coming from the cross sectional area. Okay. It is calculated from the area formula, not the volume formula. So A is equal to pi r square. We know that area is equal to 57.2 and pi is 3.4. To find the r value, take the square root of a by pi. Take the square root of a by pi. Then we will obtain the radius. So the radius is 4.72. To find the diameter, just multiply it into 2. So 4.7227 into 2 is 8.54 meter. This is how the dimension of the secondary clarifier is calculated. With the help of the loading capacity, the height is calculated. This is the water level height. By accounting the headspace height, you will find the actual height of the clarifier. Then multiply it with the cross-sectional area to find the actual volume. Then you can easily find the radius of the secondary clarifier by using the A is equal to pi r square formula. So now first one A is solved, then one B is to be solved. To find the dimension of the multigrade or carbon filter per hour, here the input stream is not only the condensate. So in this filtration setup, two different streams are entering. One is 42.9 meter cube per hour condensate and another one is 3.75 meter cube per hour, the cooling tower flow down. So the total flow rate is 46.65 meter cube per hour. Okay, this is the total volume coming inside our filtration setup. So now the volume of water is processed for 6 minutes. What is the residence time here? 6 minutes. We know that inlet rate is 46.65 meter cube per hour. So in a hour, this much meter cube is there. So for 6 minutes, how much meter cube will be processed? So 6 by 60 into 46.65 is 4.67 meter cube. This much quantity of water is processed in our filtration setup. And we know the L by D ratio given for our filtration setup is 0.8. Assuming that diameter as x, so L is equal to 0.8 into x. So the volume can be obtained by volume is pi r square h, right? So h is the L. So instead of r, we can put d by 2 the whole square. Just substitute all the values. Pi d is 0.8x divided by 2 square is 4 into h is the length, which is nothing but 0.8 into x. Substitute it. So we know the working volume now. For every 6 minutes, the volume occupied is 4.67 meter cube. Okay, this is the total volume. No headspace is there. So with the help of the 4.67 meter cube volume, you can easily find the x value now. Okay, so x is 1.95 meter. So now the diameter is 0.8 into x, which is nothing but 0.8 into 1.95. Sorry, diameter is 1.95. Length is equal to 0.8 into x. which is nothing but 0.8 into 1.95. It is given as 1.56 meter. This is how the dimension of the multigrade and carbon filter are obtained. Okay. Now, the first part of the question is solved. The second part is to obtain the amount of oxygen required in this aeration tank. For this only, we have a data which is the inlet BOD of the aeration tank is 130 ppm. Okay. So inlet BOD of the aeration tank is 130 ppm. We have to assume the permissible. We have to take the assume the outlet BOD by taking it as the permissible limit. Okay, let us assume after the treatment it is 30 ppm because it should be 30 ppm. Okay, and then the BOD removal in the aeration unit is 100 minus 30. Sorry, 130. It is a mistake here. 130 minus 30 is 100 ppm. This much amount of BOD is removed in the aeration unit. Now, we again take a assumption that for every kg, 36 meter cube of air is required. Okay, so aeration is done by using diffuser. Air requirement may be considered as 36 meter cube per kg of BOD removal. For every kg of BOD removal, 36 meter cube of fresh air is required. Okay, this is the basic amount required. Now we know that 100 ppm is removed. 100 ppm is nothing but 100 mg per liter. Okay, so mg per liter, so we can convert it easily uh, into kg per meter cube. So now 42.9 is our rate. Okay, 42.9 is our rate. So here while solving the aeration tank, what is the flow rate you have to consider is only the condensate because the cooling tower is not coming in before the aeration tank. So the flow rate is 42.9. 42.9 meter cube per hour, and now zero point 0.9 is the kg per meter cube. Sorry, zero point 0.1 is the kg per meter cube, which is nothing but 100 ppm is written as 0.1 kg per meter cube. Okay, so the BOD removed per hour is 4.3 kg. Now we know that for every hour, the BOD removed is 4.3 kg. So for 1 kg of BOD, 36 meter cube of air is required. So 4.3 kg of BOD is removed every hour. So how much air required is 36 into 4.3, which is nothing but 155 meter cube per hour. I hope it is clear. Is there any doubt in this problem? Any doubt so far? Okay.
Ma'am, please explain BOD removal. Where point
BOD.
1 you have used factor point 1 from where?
This factor. So it is from the given data only. So the only data related to BOD given is 130 ppm. Okay. So inlet BOD is given, outlet BOD is not given. Okay. So we are assuming that permissible level of BOD in the treated water after the secondary treatment is 30 ppm. So after this aeration tank, okay, so we know that inlet is given as 130. To calculate the air requirement, we should know the amount of BOD removed. Further, we should know the data of outlet BOD. So this outlet BOD, outlet water BOD is assumed as 30. Okay, this is an assumption. So the BOD removal is 130 minus 30, which is nothing but 100 ppm. How the BOD is removed? BOD is removed. BOD is the biological oxygen demand. So this oxygen demand can be removed when the oxygen is supplied. So to remove 1 kg of biological oxygen demand, it is standard that 36 meter cube of oxygen, that is air, is required. So this much air is required to remove 1 kg of BOD. Now we have removed 100 ppm of BOD. So how much air is required means this is only for per kg of BOD. but we have to calculate the total capacity also. So only we are considering the total stream. So this flow rate is multiplied with the amount of BOD removed. Okay, this is the BOD removed. For the entire wastewater stream, how much BOD is totally removed, now we have calculated. For the entire wastewater stream from the condensate unit, the total amount of BOD removed is 4.3 kg. How this 0.1 is coming means 130 minus 100 is 100 ppm. It is a unit conversion here. So it is into 100 ppm. So 100 ppm is equal to mg, right? mg per liter. So liter is converted to meter cube. So again here 10 power minus 3 will be there. And here milligram is 10 power minus 3 grams. So 10 power minus 3 and 10 power minus 3 will get cancelled. So it is equal to gram per liter. So here it is 100 ppm, 100 gram per liter. So divided with 1000. So you will obtain 0.1. Now gram is converted to kg. So this is meter cube, gram per meter cube. So this is 0.1 kg per meter cube. Understood?
Yes, now clear. Point. You directly written point one that
That is what I have mentioned here. Mg per
yeah.
liter is converted to
Okay.
kg per meter cube.
Okay. Okay.
Okay, this is how it is
Clear.
converted. Okay.
Okay.
So now for 4.3 kg of BOD removed, how much amount of air required is you have to multiply with 36 meter cube, that is constant. So 36 into 4.3 is 155 meter cube per hour. Okay. So now we have calculated the part B also. Okay. The next problem is if the average heat rate of a cogen power plant is 2611 kilocalories per kilowatt hour, calculate the average efficiency of the plant. Okay. This is a very simple problem. Okay. The formula given is for thermal efficiency and the data given is only one data, which is nothing but the average heat rate. They are asking you to calculate the average efficiency of the plant. Okay. To calculate the thermal efficiency, the formula is efficiency is equal to energy generated into time divided by MC into CV. So MC is the quantity of fuel per feed consumed. For this much amount of feed, how much amount of fuel is produced. That is the MC. And CV is the calorific value of the particular feed. Okay. So with this formula can be rewritten as whatever is written in this numerator, that is energy consumed in energy generated into time, can be written in the denominator like MC into CD divided by energy generated into time. That is what written here. Okay. So 1 by energy generated into time, when it goes above, it will be energy generated into time. The formula is same. You are just rewriting it. Okay. Now this is explained in terms of HR. So this HR is nothing but the average heat rate. Okay, that is what this formula is rewritten. So 100 divided by the average heat rate is what the thermal efficiency. This is the another form of writing the formula. So now we should be writing calculating the thermal efficiency. So efficiency is normally unitless one. It is written in percentage. For that, what we have to do means so this HR is given in kilocalories per kilowatt hour. To convert the kilowatt hour to kilocalories, you have to multiply it with 859.8456. So you will obtain the value of 33%. Okay, so kilocalorie and kilocalorie will get cancelled after converting the unit. Finally, you will obtain the thermal efficiency also. Okay, is that clear? Next problem is based upon the chromium removal, and the last problem is also chromium removal. Okay, these are all very simple problem only. Only the distillery unit is a big problem. Now coming to this question, the flow rate of the chromium bearing wastewater from a tannery unit is 2 kiloliter per day, contains the chromium concentration CR3 plus as 20 mg per liter. The efficiency of chromium recovery unit is 95%. Calculate the amount of fresh chromium sulfate required. So, we have discussed that whatever the wastewater stream, okay, is produced from the tannery unit is classified into two types. One is chrome based and another one is non-chrome based, right? Non-chrome based. So chrome based means it contains the chromium. Non-chrome means no chromium is present. This is the wastewater produced from other steps, okay, not the tanning step. So here in this chrome based, chromium is recovered by using magnesium oxide and sulfuric acid, H2SO. With the help of this, the chrome-based wastewater, first we will obtain the chromium hydroxide. Okay. Chromium hydroxide is removed, and then this chromium hydroxide is formed into chromium sulfate. CH53. Chromium hydroxide is converted to chromium sulfate. This is the process. We have to keep this in mind to solve these problems. Now coming to the data given, the chromium concentration in the wastewater. The concentration is 20 mg per liter and the efficiency of chromium removal is 95%. Okay. By using these chromium treatment tank and chromium recovery tank, we are removing 95% of the chromium or capture. Okay. So, amount of chromium removed from the stream 2 kiloliter per day is calculated now. So, which is nothing but 0.95, 95 by 100 into 20 mg per liter. This is in mg per liter and this is in 2000. 2 is written as 2000 liter per day. Now, liter will get cancelled and we will obtain the unit mg per day. So, by multiplying 0.95 into 20 into 2000, we will obtain 38,000 mg per day. This is the 38 grams of chromium removed, that is recovered every day. So, amount of chromium lost. So, in the stream, 5% is not removed. So that is the loss. So the chromium loss is calculated now, which is nothing but 0.05 into 20 into 2000. That is nothing but 2 grams per day. So 2 grams of chromium are lost. So the molecular weight of the chromium sulfate Cr2SO4 thrice is 392 grams. Okay. So in the 392 grams, 104 grams of chromium ions are there. Okay. 2 Cr2 are there. So the total weight is 104 grams. So you have to calculate how much amount of fresh chromium sulfate is to be added every time after the recovery. So 2 gram is lost. So 2 gram into 392 by 104 will give you 7.5 grams. So you have to add 2 gram of chromium every day because it is lost. But chromium is not added directly in the form of chromium. It is added to the tannery process in the form of chromium sulfate. So you have to calculate this 2 grams of chromium in terms of chromium sulfate. So we are using the stoichiometric balance. In 392 grams of chromium sulfate, 104 grams of chromium are there. Okay. For 2 grams of chromium, how many grams of chromium sulfate is required means we have to just divide 392 with 104 and multiply it with 2 grams. So finally, you will obtain 7.5 grams of chromium sulfate per day. This is required. This is to be freshly added to restore the process. Okay. I hope it is clear. And this is also a similar question, but it has some extended other kind of question also. Okay. The question is the flow rate of the wastewater from a tannery industry is 2 kiloliter per day and it has the chromium content. Here the chromium concentration is 15 mg per liter. Okay. As per the CPCB standard, the effluent should not contain total chromium more than 2 mg per liter. So the standard value is after the treatment, the amount of chromium of the effluent should not exceed 2 mg per liter concentration. Now the rate of the chromium removal in gram per day required in ETP is to be found. Okay, that is the first question. If 90% of this chromium is recovered, so they are telling that 90% is the recovery percentage. How much amount of MgO is required? As we have discussed, in the recovery of chromium, we are using MgO and hydrogen, sulfuric acid. So how much amount of magnesium oxide is used in this process to recover this chromium? They are asking. Two questions are there. One is find the rate of chromium removal. Amount of Cr3 is removed. Okay, that is the first question. And the second question is amount of MgO used. Okay, that is the second question. So, writing the data given, influent chromium concentration is 15 mg per liter and the effluent chromium concentration is the threshold limit, okay, 2 mg per liter. Now, the flow rate of the influent wastewater is also given, 2000 liter per day. Now, the rate of chromium removal, in a similar way, we have to calculate. The rate of chromium removal, how here it is calculated, we have to calculate. So, it is 15 minus 2 mg per liter. This is the amount removed. Okay, 15 minus 2 mg per liter into 2, okay, into 1000 mg per day. It is nothing but 2000 mg per day. That is the flow rate of the influent wastewater. So you will finally obtain amount of chromium removed as 26 grams of chromium per day. Amount of chromium removed is 26 gram per day. Amount of chromium recovered is, so in this removal stream, only 90% is recovered. So multiply it with 0.9. So 26 into 0.9 is nothing but 23.4 grams of chromium recovered per day. Okay. With this, again, you have to calculate this in terms of chromium sulfate. You know that for every 392 grams of chromium sulfate, 104 grams of chromium are there. For 23.4 grams, how many grams of chromium sulfate is required? It is nothing but 88.2 grams of chromium sulfate per day. So this is the first part. Okay, in the first part, the chromium recovered is calculated. Now, why the chromium sulfate is calculated means to obtain the MgO value. So again, it is obtained by the stoichiometry. Okay, so stoichiometry is very important to solve these kind of problems in today's lecture. It plays a major role here. So this is the standard equation, stoichiometric equation. So we use 3 moles of MgO for every mole of chromium sulfate to form 2 moles of chromium hydroxide and 3 moles of magnesium sulfate. Okay, this is the stoichiometric equation. How the chromium sulfate is converted to chromium hydroxide is given by this equation. Now, why our chromium sulfate calculation is essential means we know that for 392 grams of chromium sulfate, how many grams of MgO is required means 3 into 40, that is 120 grams of magnesium oxide is required for the treatment process. So for 392 grams, 120 grams are required. So for 88.2 grams, how many grams are required means, so we have to multiply it with 88.2, which is nothing but 27 grams per day. So 27 grams of MgO is required for the treatment of 88.2 grams of chromium sulfate. Okay, this is the part 2. Do you have any doubt in this question? We have calculated the chromium recovery in this 2 question. Additionally, we have calculated how much magnesium oxide is used for this chromium recovery. Any doubts? Your mic is muted, Jyobi.
No, ma'am. Okay.
Okay.
In the previous one question you have used in, there was a cooling tower or blow down. what it terms mean in problem
What?
it state
This one.
blow down. Yeah.
1 minute.
Uh,
The CPU unit
one
you are asking.
tutorial. Yeah, yeah.
Okay, okay. This is the fermenter cooling tower and the distillation cooling tower. Whatever water coming from it is called as blow down. Okay.
Blow down means what? What no, it's the process or what is? What do you mean by blow down?
Blow down is nothing but the amount of water spent for this is again taken for the treatment. No, whatever is used for the cooling process.
So this well, this term we use while calculation.
No,
Cooling tower
this
loop.
this term is not used for the calculation. Like
Okay.
how much water is blown down is not calculated here. Okay, this
Okay.
is the term where it is mentioning the two streams. One stream is named as condensate, another stream is named as cooling tower blow down. Okay, we are not calculating the water blow down. The data is given directly. What is the flow rate of these two streams is the data given. Okay,
Okay. That was a little confusing. That's why I asked. Okay,
okay.
no problem.
Two
Yeah.
streams
Thank
are
you.
there. Yeah,
Okay.
I will show you this process diagram. Um, so if you see here, we have two different streams. One is the MEE stream and another one is this CPU stream. Okay. So this MEE stream will give you the condensate. Okay. And to this CPU stream only, all these fermenter cooling tower and distillation cooling tower water will come. These two streams are separate stream in the distillery process. Okay. You can just keep in mind that two different streams are there in the distillery unit. Okay.
Okay, ma'am. Clear.
Okay. Thank you.
Thank you. Thank you.
Okay. Thank you for joining. We'll see you in the next Saturday session from 3 p.m. to 5 p.m. Thank you.
Okay. Thank you, ma'am. Thanks.